So when interest is compounded quarterly, that's 4 times a year, you need to divide that interest rate by 4. If your interest rate, if you're going to compound monthly, you're going to divide that interest rate by 12. So here's a little table that shows you. If we are compounding our interest annually, we're going to take that annual interest rate, so 0.08, and divide it by 1, which is the same thing as just 0.08. Semi-annually, let's change our color right here. Semi-annually means twice a year. So you're going to take that interest rate and you're going to divide it by 2. Quarterly means we're going to divide that interest rate by 4, because quarterly, 4 quarters in a year, and monthly, there's 12 months in a year. So monthly, we're going to divide that interest rate by 12. And I'll show you, we'll put this into action in our problem. Compound interest. Suppose your parents deposited $1,500 in an account paying 6.5% interest, compounded quarterly, which is 4 times a year, when you were born. Find the account balance after 18 years. So our initial value is going to be $1,500. Another important piece of information is our interest rate. So we're going to be earning 6.5% interest. And then, very important, that's going to be compounded quarterly. And we're going to keep that money in the account just sitting there for 18 years. So our balance is going to equal our initial amount times 1 plus, I can't just put 6.5% or 0.065. I can't just put that because I have to take that and I have to divide it by 4. Now, if I divide that amount by 4, that means they're not looking at my account 18 times for 18 years. They're looking at it 4 times a year for 18 years. So they're looking at it 4 times 18 times. 4 times 18 times. So we're going to write this. I'm going to take this and I'm going to move it for a moment. This x value that I'm going to put here, that x value is going to represent the number of times the bank is going to pay you interest. The bank pays you interest. And every time they look at your account, they're paying you interest. So they're looking at your account quarterly. So 4 times a year for 18 years. And that's why when we want to find the account balance, in place of x, we're going to put 4 times 18. So here's our function. Our function is going to have an input and an output. And then we're going to use that function to find out what our account balance is. So the account balance is going to be approximately, now what I would do is I would probably put this into my calculator first. So in the calculator, I would do what's in parentheses first. 1 plus 0.065 divided by 4. And if I really wanted to do order of operations and not make my calculator do it for me, I'd say 0.065 divided by 4, because you have to do the division first, then add the 1, you're going to get a number. That number right there, let me pick a color that has not been picked. There we go. So this value right here is the same thing as this. Then you're going to take that amount and you're going to raise it to the 4 times 18 power. So in parentheses, you're going to put 4 times 18. Very important that you put parentheses there, because if you don't put parentheses, it might just raise it to the 4th power and then multiply your result by 18. We want to take this value and multiply it by itself 72 times. So 4 times 18 is 72. You could put upper caret 72, or you can put upper caret parentheses 4 times 18. That's going to calculate this part for you. So this right here does all of that. Then you're going to take in your calculator and you're going to hit times 1500. And when you put that into your calculator, the way I've just told you to, you should get $4,787.75. So if you got that amount, then you put it into your calculator properly. Yay for you. Give yourself a pat on the back. You did it. Okay, now you get to try compounded monthly. Same amounts, just this time instead of compounded quarterly, we're going to compound it monthly. Okay, so press pause. If you've already pressed pause, I'm going to show you what the answer is for A. We're not going to do B. We're just going to do A. So for A, and this was for example number 5, I think. We're going to have y equals the same amount, 1500, times 1 plus 0.065, but this time we're going to divide it by 12 for monthly. That means we're going to be looking at the account 12 times a year for 18 years. That would be 12 times 18 in parentheses. And then you put all that in your calculator, and this is going to tell us whether or not you've got your calculator strokes down properly, is to putting everything in the order it needs to be in. And $4,817.75 is our answer. Hip, hip, hooray. Okay, we've talked about exponential growth and exponential decay. And here's a couple of examples. One example of exponential growth. Notice how your base is greater than 1. And then here we have exponential decay. Notice how the base is less than 1. So when B is greater than 1, we've got growth. And when B is less than 1, we have decay. And when I talk about B, we're talking about y equals A times B to the x. So the half-life of a radioactive substance is the length of time it takes for 1/2 of the substance to decay. So what's going to go in parentheses is the amount that's going to remain. So think about when we were at the copier and we were reducing to 90%. We reduced, I'm going to go to another page here because I don't want you to. When we went to the copier and we did 90%, that means we reduced by 10%, and we retained 90%. And what was that base? That base was 0.90. Remember? It was 0.90. So this base is going to be what you retain. When you retain less than 100%, it's decay. So sometimes the problem is going to tell you what they're reducing it by. You have to get this value. Okay, so let's go back here. Half-life of a radioactive substance is the length of time it takes for 1/2 of the substance to decay into another substance. So to treat some forms of cancer, doctors will use radioactive iodine. The half-life of that iodine is 8 days. So that means it goes into the patient, and 8 days later, half of it is gone. It's been absorbed by the patient. So that's how they know whether or not when to give you another treatment. Okay? Patient receives 12 millicuries, a measure of radiation treatment. How much iodine is left in the patient 16 days later? So we start with y equals a times b to the x. X is going to be the number of, not years, not minutes, not hours, it's days. Number of days after the initial treatment is given, right? And our output is going to be the amount of iodine remaining in millicuries after X days. We need to figure out what our initial amount is and what our decay factor. In this case, it's not a growth factor, it's a decay factor. So your decay factor is how much remains, the amount remaining. So y is going to equal, well, what are we starting with? What's the initial amount? The initial amount is going to be the amount of millicuries that the patient is given. So that's going to be 12 millicuries. And then how much remains in the patient? That's going to be 1/2. Now X is the number of days after the initial treatment, right? But you can't just say to the X power, because when is it getting cut in half? Every 8 days. So after 8 days, it's cut in half. So I have to have X over 8 here. Okay? X is the number of days after the initial treatment. If I go the full 8 days, then I know that I'm only going to have 6 millicuries left in my body. If I go 16 days, that's 2 half-lives. It was cut in half twice, right? So y is going to equal 12 times 1/2 raised to the 16 over 8 power. That's going to be 12 times 1/2 raised to the 2nd power. So that means I'm going to start with 12, and then remember our geometric sequences. This is 8 days later. We have 6. And then another 8 days later, we're going to have 3. So I can do this without using the formula, but the idea is that I'm going to need to use the formula at some point, because I need to grow on this concept. I need to build on this concept. We're going to start with it in Algebra 1, and then we build on it in Algebra 2, college algebra, pre-calculus, calculus. So it's important that we understand how we translate that to an algebraic equation or function. So that means I'm going to multiply by 1/2, not just one time, but 2 times. So that's going to be 12 times 1/4, which is 3. And we knew that, 3 millicuries after 16 days. Now, those of you who are thinking about maybe going into nursing, being able to do this calculation is really important. Understanding the calculation will help you. It will help you be a better nurse in your job because it will make sense to you why it is that these calculations are so important, because it could mean someone's health. It could mean helping a patient get better. It could mean potentially helping them get sicker, and we don't want to help them get sicker. We want to help them get better. So we really need to know our numbers, our math. Okay, how many half-lives of iodine occur in 32 days? So how many half-lives? So we have y equals, right, your initial amount. Y equals our initial amount times our decay rate raised to the x over your, I guess we could say, you could say the number of half-lives, right? So how many half-lives would occur in 32 days? Well, 32 divided by 8 days, because 8 days is your half-life. So if I have 32 days, I'm going to end up having 4 half-lives. It's going to cut in half 4 times. So rather than go off to the side and say 4 half-lives, right, we can just incorporate this, divide by 8 into our function. So that's what I did there. Y equals a times b raised to the x over 8. And now if it doesn't happen a perfect number of times, let's say I said 20 days, right? I could still do 20 divided by 8 and figure out how much is still left in the patient's body so that I don't give them another course of treatment too soon. So let's do this problem right here. Suppose you start with 50. So how does our equation change if we start with 50 millicuries? Well, A becomes 50. And then our half-life, we're still going to have half remaining after a certain amount of time. How much iodine is left after 1 half-life? So after 1 half-life, that would be 8 days out of 8 days. Okay, so that's 1 half-life. How much would be remaining after 2 half-lives? So 2 half-lives, I'll do in blue here. That would be y equals 50 times 1/2 over 1/2 raised to the 16 over 8. That would be 2 half-lives. So where is this coming from? 1 half-life, 8 over 8. 2 half-lives, 16 over 8 is 2. The chances of things falling into perfect half-lives, slim to none. And that's why we're setting it up this way with the x over 8. So with 1 half-life, I got 25 millicuries. And with 2 half-lives, I got 12.5 millicuries. Cesium-137 has a half-life of 30 years. So now we've got a new problem. So here's C. Suppose a lab stored 30 millicuries in 1973. how much will be left in 2003 and then in 2063. So a half-life of 30 years. So that means y equals, I'm going to have a times 1/2, or half remaining after every 30 years. So x over 30. Suppose a lab stored 30 millicuries. So we're going to have 30 for our initial value times 1/2 raised to the x over 30. That was in 1973. Therefore, x equals the number of years after 1973. How much will be left in 2003? Well, 2003, x would equal 30 because that's 30 years after 1973. So in 2003, that would be 1 full half-life. If it happens every 30 years, then I'm going to end up with 15 millicuries left. Now, what happens in 2063? Well, that would be 90 years. So how many half-lives would that be? Y equals 30 times 1/2 raised to the 90 over 30. That right there is 3 half-lives. So y equals 30 times 1/2 raised to the 3rd power, which is 30 times 1/8, which is 15 over 4, which is 3.75. So 3.75 millicuries. Is it millicuries? Yeah, millicuries. We're measuring it in millicuries. So there's our two answers. So in 2063, 3.75. In 2003, 15 millicuries. This is some serious stuff. We're really, really, really in the big time now when we're talking about our exponential functions. So that's our exponential decay when it comes to half-lives. We're going to finish up in the next talking about the decay factor when we're not talking about a half-life.